Hello everyone, myself Dr. Amit Kumar Yadav, Associate Professor, School of Computer Science and Artificial Intelligence, SR University, Warangal, Telangana, India. Today we are going to explore a very powerful in AI counterfactual explanation, also called what if approach. This concept helps us answer one important question: what need to change to go a better result? And this is something that applies directly to your academic life as well. Counterfactual with minimal changes, the what if game. How can the smallest possible change lead to a completely different results? So let's begin with simple idea. The smallest change can sometimes create biggest difference. Imagine this: your toy broke. You want to fix it. What's the smallest change you can make? Maybe just reattach a loose piece or replace one small part. Counterfactuals work the same. Find the smallest possible change that leads to a different outcome. Now, not a full rebuild, just a minimum tweak needed. In another word, we can say that imagine your toy is broken. Do you rebuild the whole toy? No. You fix the smallest part, maybe just one loose part. That's exactly how counterfactual work. Find the minimum changes needed to fix the outcome. Example: getting a better grade. The situation: you got a C on test. You want an A. What's the minimal changes that would have made the difference? The counterfactual: if I had studied just 2 more hours, I would have gotten an A. That's it, one small, specific change. No need to rewrite your entire study plan. This precise insight is what makes counterfactual so actionable. Why does it matter? Understand the why. Counterfactuals reveal the root cause behind the decisions, not just the outcome. Know what to change. They give you a clear, actionable path to a better results. A detective for decisions. Like a detective, counterfactuals trace back what went wrong and what could fix it. Why is this important? Because it helps you understand why something happens, know exactly what to change, think like a detective, finding the root cause, not guessing but solving. Counterfactuals for structured data, like a spreadsheet detective. What is structured data? Think of a spreadsheet or database. Rows represent peoples or items, and columns hold details like age, income, or city. A loan application is a classic example. One row per applicant, with column for income, credit score, employment status, and requested loan amount. So we can say that in structured data, first imaging a table, each row is a person, each column is information, income, marks, attendance, all uses this structure to make decisions. Example, loan application denied. What happened? The system says income too low. The loan was denied. No further explanation given. Frustrating and unhelpful. The counterfactual explanation. If your income has been $10,000 higher, your loan would have been approved. Now the applicant knows exactly what to change. A clear, specific, and empowering insight instead of a dead. So loan examples. So let's say your loan is rejected. The system just say income too low. That's not helpful. But a counterfactual says if your income was say $10,000 higher, it would have been approved. Now you know exactly what to improve. How it works. Simply put, find nearest example. Locate the closest approved case. Measures smallest difference. Compute the minimal gap precisely. All examines data. Analyze your spreadsheet inputs. Return that difference. Provide the gap as your explanation. The AI finds the nearest successful data point and measure the minimal gap between it and your case. So we can say here the simple process. AI look at your data and it find a similar successful cases. It measures the smallest differences, give the differences as advice. So instead of confusion, you get clear directions. The counterfactuals in reinforcement learning, teaching a robot what if. Now let's moving into something more advanced, reinforcement learning. What is reinforcement learning? It's how AI agent like robot or game character learn through trials and errors. Good action earn reward, bad action bring penalties. The goal: learn the sequence of actions that earn the most reward over time. Good action reward, bad action penalties. So we can say say in reinforcement learning, this is how AI learn through reward for good actions, penalties for bad action, like how human learn through experience. Example, a robot learning to walk. What happens? The robot took a step and fell over. A penalty without explanation. It just tries again randomly, wasting time and effort. Counterfeit question. What if the robot has adjusted its knee angle by just 5 degrees? This target insights helps the robot understand why it fell and exactly how to correct its next attempt, accelerating learning dramatically. So we can say that in another word, imagine a robot learning to walk. It takes steps and falls, Without explanation, it keeps guessing. But with counterfactual thinking, what if the knee angle with 5 degrees different? Now learning become faster and smarter. Counterfactual make RL smarter. Action taken, the agent choose action A and receive a low reward. Counterfactual insight, if I had chosen action B, my reward would have been higher. Improved policies, the agent update its strategies, learning faster and more transparently. Counterfactuals don't just speed up learning, they make AI reasoning understandable to human. Counterfactuals improve by learning by saying, if I had done this instead, I would get a better result. So the system learned faster, more clearly, more intelligently. Now let's move to time series data predicting the futures. What is time series data? It is data collected in sequence over time, a series of measurements taken at regular intervals. Each data point depends on what came it before. Stock prices rises and falling daily. Weather temperatures hour by hours. Patients' heart rates during surgery. Website visitor traffic each minute. So in another word, we can say that time series means data over time. Example, stock prices, weather, heart rate. Each value depends on the past. The challenges, when something changes. Normal pattern, steady demand predicted from past data. Disruption, heat wave cause sudden unexpected spike. AI models predict futures value based on past patterns, but the real world throws surprise. A sudden heat waves, a market crash, a viral trend that break those pattern entirely. Without counterfactual tools, we can't easily explain why a prediction change or what external factor causes. So we can say here, counterfactuals improve learning by saying it had if I had done this instead, I would be better result. So the system learn faster, more clarity, more intelligent. Counterfactual for time series in action. If the temperature has 5-degree lower yesterday, electricity demand would have been 10% less today. Researchers are actively building tools for exactly these methods, like forecast CF, GenFact, generate realistic counterfactual scenarios for time series prediction, helping us understand the true fact of a specific event on future outcomes. So we can say here counterfactuals help us explain cause, effect, and impacts. Making explanation plausible. Changing number is not enough. The change makes sense in the real world. A stock price doubling overnight or a temperatures dropping 50 degrees in an hour are not plausible counterfactuals. New research focuses on plausibility constraint, ensuring counterfactuals stay realistic, respecting natural limits and temporal patterns in the data. Bad implausible, sudden, impossible stock spike, gradual, realistic temperature change, good plausibles. So plausibility, but one important rule, changing must be realistic. We cannot say temperature drop 50 degree in 1 hour. So counterfactual must be plausible and practicable. Real world impact across industry. Healthcare. If this patient blood pressures hadn't spikes, their heart attack risks would have been 30% lower. Finance. If interest rate had not changed last quarter, the stock value would have remained stable. Business. If we had run this ad campaign for one more week, salaries would be increased by, say, 15%. So let's see where this is used. Healthcare, understanding risks. Finance, predicting investment. Business, improving sales. This is not theory, this is a real world impact. Conclusion. So, counterfactual explanations are one of the most powerful tools for making AI understandable, fair, and actionable. By asking the right what if question, we can learn from past, make sense of the present, and build a smarter, more trustworthy system for the futures. Minimal change, small tweak, big insights, structured data, spreadsheet detective work, reinforcement learning, smarter robot faster, time series, realistic futures scenarios. So, what is the key takeaway? Small change can create big outcome. Counterfactuals help us learn from the past, understand the present, improve the future. Final thought, always ask yourself, what can I change to do better? Because the questions lead to success. Understanding AI, how graph think and why we need to know. The topic graph neural network and more importantly, how we can explain their decision using tools like GNN explainer and node importance attribution. By the end of this lecture, you won't just know what AI predict, you will understand why it predicts. Why graph based explanation? Before we trust AI, we need to understand how it reasons. Many modern AI systems are extremely powerful but also opaque. Graph give us a way to open the black box and trace reasoning step by step. What is graph? Think of it like a social network. Nodes, the thin people, cities, atoms, base, each node represent one entity. Edge, the connection, friendship, roads, chemical bonds, edge like nodes together. A graph is simply a way to represent relationship between things. Think of your social media. You are a node, your friends are nodes, and each friendship is an edge. Graph let AI see the world the same way. So, in another word, we can say that a graph is just a way of representing a relationship. Think of a social networks. You are a node, your friends are nodes, your friendship are edge. This structure allows AI to model connection, not just isolated data points. Why use graph in AI? Real world data is rarely isolated, it's deeply connected. Graph let AI capture those connections naturally. Social network, who is friend with whom? Graph map relationship between millions of users. Molecular structures, how are atoms bonded? Graph model chemical compound for drugs discovery. Recommendation system, what products are similar. Real world data is really independent, it's convenient. Graphs are useful in social network, molecular molecules in chemistry, recommendation system. In all these cases, relationship matters as much as data itself. The challenge is AI can be a black box. Complex AI models like graph neural network can make remarkable accurate prediction, but explaining why they reach that conclusion is another story entirely. It is just like asking a friend why they recommend movie and they just say because. That's not good enough, especially when the stakes are high. Here input graph data goes in, black box hidden reasoning, output prediction comes out. The black box problem. Here the challenge is AI models, especially graph neural network, can make highly accurate predictions. But when we ask why, we often get no clear answer. This is what we call the black box problem. Input goes in, prediction comes out, but the reasoning is hidden. Explaining AI why it matters. Trust. In high stake fields like medicines and finance, we must trust AI decisions, and trust requires transparency. Debugging. When AI make a mistake, explanation help us pinpoint exactly where the reasoning went wrong. Discovery. Good explanation can reveal surprising new insights hidden within complex data. Now here we can say that why should we care about explanation? So there is three key reasons. Trust, especially in medicine or finance, debugging to fix error, discovery to uncover new insights. Without explanation, AI is just guesswork. Transition to GNN explainer. Now that we understand the problem, let's look at one powerful solution, GNN explainers. What are graphical neural networks, GNNs? So GNNs are especially AI models built to work with graph structured data. What it is doing, it learns by combining two sources of information, node features, properties of each node like a person's age or an atom type, graph structure, who is connected to whom, the edge. GNNs pass messages along edge, allowing each node to learn from its neighbor. Over multiple rounds, they build a rich understanding for entire graph. In another word, we can say that graph neural network are designed especially for graph data. They learn from node features like age or atom types, graph structures, connection between nodes. They work by passing messages between nodes, allowing each node to learn from its neighbors. The problem with GNN complexity, features plus structure, powerful prediction, opaque black box, hard to explain. The very thing that makes GNN powerful is ability to blend node features with graph structures is also what makes them so difficult to interpret. We need dedicated tools to crack them open. So the power of GNNs comes from combining structures and features across multiple layers. But the same complexity makes them very hard to interpret. So we need specialized tools to understand it. Introducing GNN E-Explainer. GNN Explainer is a model agnostic tool. It means it works with any GNN that acts like detective for AI predictions. Its mission is to identify the most important part of graph and this leads to a specific outcome. First of all, any GNN model, it works regardless of GNN architectures. Any prediction, it explains node, edge, or graph level output. Visual results deliver human readable visual explanations. So GNN explanation act like detectives. It work with any GNN model and explain any prediction. Its goal is simple. Find the most important part of the graph responsible for decisions. How GNN explainer works. Here input graph, search minimum, return explanation. Think of GNN explainer like a detective that crime scenes. He searches through all clues, nodes, and edge to find the minimum sets of evidence that explain the verdicts. So here, in another word, we can say that imagine a crime scene investigation. Investigation. GNN explainer search through all nodes and edge to find the smallest set of evidence that explain the output. Technically, it learns a marks that highlights the most important subgraph without retraining the models. What GNN explainer gives us? Compact subgraph, a small relevant slice of original graph that capture most structural relationship. Keynote features. The specific characteristic like atoms type or user's age that combine most to the predictions. Visual explanation. It highlighted graph you can actually see an interpretation making AI reasoning human readable. What do we get from GNE Explainer? A compact subgraph, important node features, visual explanation. So instead of guessing as we see the reasoning. Benefit of GNN explainer interpretability. Understand why a GNN made a specific prediction, not just what it predicts. Visualization. Here we have to see GNN reasoning laid out as a highlighted subgraph. Error analysis. Here identify flaws logic in GNN before it causes real world. That is 17.1% average improvement over baseline explanation method in benchmark studies. GNN explainer consistently outperform baseline methods, making it one of the most trusted tools for GNN interpretability. We can say here why is this powerful because it improves interpretability, visualization, error detection. It even outperforms many baseline explanation methods. Node importance attributes, pinpoint, key, key player. Now let's go deeper. Instead of looking at subgraph, what if you want to know which individual nodes matter the most? That's where node importance attribution come in. What is node importance attribution? Node importance attribution is a way of explaining GNN prediction by quantifying exactly how much each individual node contributed to the final outcome. Imagine a group project. Some member did most of the work and some contributed very little. So here node attribution is the tools that fairly assigns credit or blame to each participant. In an in another word, you can think of it like a group project. Some member contribution more than other. Novel attribution assign credit or blame to each node based on its contribution. GOAT, a new way to attribute graph output. So GOAT here means graph output attribution is a cutting edge method that directly link a GNN predict back to specific input features, node and edge with remarkable precision. It includes faithful discriminative tables. So here we can say here one advanced method is good, that is graph output attribution. It is faithful discrimination stable. It directly link prediction to its peak nodes and features. How GOAT works? GOATs break down the model's computational into smaller parts. Each part is tracked back to nodes and edge, giving precise importance scores. Unlike GNN explainer, it doesn't search, it calculates directly. Why node importance matter? This gives us very detailed insights. Which node matter most? Which features influence prediction? more reliable, evaluated of modes. It is like zooming into a reasoning process. Let's bring it all together. Graph model connected data. GNN learns from those connections. GNN explainer shows key subgraph. Node attribution shows individual contributions. So together they turn AI into something that we understand and trust.